Okie dokie, chemists, we're gonna get started now. Yeah, we'll get started. Good morning, chemists. We'll get started now. So, yeah, plan is we'll finish up chapter 8 today. We left off talking about Lewis structures and drawing correct Lewis structures and the 6 steps to achieve that. But just to summarize, kind of our placement in this chapter. Earlier in this chapter, in chapter 8, we talked about bonding in ionic compounds. With Lewis structures, we're looking at bonding in molecular compounds. So let's remind ourselves the difference between those two. We talked about naming ionic compounds and molecular compounds in chapter 2. It's all based upon composition. Ionic compounds were metal, non-metal, typically forms ions. So we looked at lattice energy earlier in this chapter, and we were able to predict magnitude of lattice energy given different charges and different formulas for ionic compounds. Now we're looking at Lewis structures in building molecular compounds. So notice that everything we're doing here with Lewis structures contains entirely non-metal compounds. So this is where we get our Lewis structure molecules that we know to contain all non-metal materials, versus ionic compounds had our metal and our non-metal. So we left off practicing our 6 steps to Lewis structures. If you master these 6 steps, you will always be right. And so we looked at this example, CO2, and went through the 6 steps to determine what is the correct Lewis structure for CO2 or carbon dioxide. So let's just go through these 6 steps again. So let's remind ourselves the 6 steps. The first one is count number of valence electrons given the actual chemical formula. So I give you CO2 here. We have 1 carbon atom, which gives us 4 valence electrons, and 2 oxygens that give us 6 each. So we are allowed to place a total number of 16 valence electrons. I like to think of that number as like money, all right? And that's how many electrons we are allowed to spend in this picture that we draw. You adjust charge if there's a charge present, but since CO2 is neutral, we don't have to do anything. So 16 is the number we're going to work with. Next, we draw our skeleton structure, where typically the central atom is written first in the chemical formula, and if not, we usually tell you what the central atom is. So since carbon is written first, we're going to write that one in the center, and we're going to draw the oxygens on the outside. So what I mean by skeleton structure is carbon goes on the inside, oxygen on the outside, and then you draw single bonds to each of those things. So remember, in a bond, a single bond contains how many electrons? 2. So just drawing those 2 bonds takes away 4 electrons out of our 16 electron count that we're allowed to use. That's important because in the next step, we're going to place those leftover electrons on outer atoms first, completing octets as needed. All right, until we run out of electrons. So I did that here where I placed the electrons completing the octets around those oxygen atoms. And then finally here, you place electrons on the inner or the central atom, but only if you have leftover electrons. So if you count how many electrons are drawn right now, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So am I allowed to put electrons on the central carbon? We are not allowed to put any more electrons because we've run out of electrons. But notice here, does this carbon have a complete octet? It does not. So high school me used to just draw more electrons on it and be like, oh, nope, now the octet's complete, right? But we can't draw those additional 4 electrons because we've run out of electrons. So how we get around that is this last step. We're going to place multiple bonds in order to help that central carbon achieve its octet. And so I don't mean just draw additional bonds, because just drawing those bonds places more electrons we don't have. So what we're going to do is actually just rearrange some of the electrons that are already there. But there's something kind of weird about this. There's a couple ways we can actually do that. One of the ways is the most obvious way is, let's take that lone pair of electrons on one of the oxygens and make a double bond. And let's do the same thing over here, right? So I'm not drawing any new electrons. Really what I'm doing is just rearranging electrons that are already there. So there's double bonds there, but then how many electrons, how many lone pairs are left on this oxygen right here? 2, yes, because I just moved a lone pair to make a double bond, right? So there's 2 lone pairs there, and then there's 2 lone pairs there, all right? So that, we just moved electrons around to complete carbon's octet in the center. But let me ask you, there's actually another way we could complete carbon's octet. It just needs 2 double bonds or 2 additional bonds to it. So technically, couldn't I also just do this? I could move this lone pair, make a new bond with an additional multiple bond with carbon, and couldn't I also move that lone pair? So let's draw what that would look like, where carbon is still in the center. There's now a triple bond here. Oxygen is on the outside, and then how many lone pairs are left on this oxygen? Just 1. And then the other oxygen, we didn't do anything to it, so I'll just redraw it like that, right? So I'm going to ask you, you might be looking at these 2 structures and you might think, oh no, one of those is clearly correct, but why is it correct? Because I ask you, look at this second structure of CO2 I drew. Does every atom have a complete octet? Ask yourself. Are you sure? Let's look. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons. This central carbon, how many bonds are to it? 1, 2, 3, 4. So that carbon has 8 electrons. And what about this oxygen? Yep, that every single atom in this structure technically has a satisfied octet. So how can we know for certain that this one is wrong? And it has to do with formal charges. This structure is wrong because it does not minimize formal charges. So that's what we learned about in the previous slide up here, all right? Where we can calculate and assign formal charges for individual atoms in a drawn Lewis structure, and where our most correct Lewis structure is the structure that minimizes formal charges, meaning 0 is preferred. So let's just go ahead and calculate what are the formal charges of all of these atoms in the Lewis structures that we've drawn. So formal charges is, to calculate it, when we do it for each atom, is you want to start, think about how many electrons are typically around each of these atoms. So what you're going to do is tell me how many typical valence electrons are on that atom, and then you're going to subtract how many electrons are on that atom in the Lewis structure, number of electrons that atom has in the Lewis structure. And I'll show you how we do that. All right, so how I like to approach this is look at the electrons that make up all of these chemical bonds and have those chemical bonds like get a divorce, and all the electrons go back to its original atom. So each of those chemical bonds have 2 electrons in them, but they're going to go each with 1 atom and then the other electron with the other atom. So I like to draw it like this, where here are the 2 electrons on oxygen and carbon, but they're going to go back to their respective atom. Same thing here. And then we're going to do the same thing here. So the 4 electrons, they're just splitting up. They're getting a divorce going each with each atom. And so when you do it this way, it's very easy to draw a box around each of these atoms to say, okay, these are all of the electrons assigned to each of those atoms. All right, and you can count how many dots, how many electrons are assigned to this oxygen. It's 1, 2, 3, 4, 5, 6. In this carbon, 1, 2, 3, 4. In this oxygen, 1, 2, 3, 4, 5, 6. All right, so all of those numbers are this subtraction value. So let's just go ahead and calculate the formal charges here. All right, so what we're going to do is determine how many valence electrons are typically on these atoms. So oxygen has how many valence electrons, just right off the periodic table? 6, and then carbon has 4, and then oxygen has 6, all right? So those are just the numbers straight off the periodic table. Then you count the number of electrons each of those atoms have on the picture, on the Lewis structure that we've drawn. So I ask you, how many electrons are drawn inside this oxygen box? 6, and then for the carbon, 4, and then 6. So when we subtract these numbers, we get a bunch of zeros. Is that good? That is good. 0 is good for formal charges, all right? So let's do it again for the wrong structure, all right? We're going to do it again for the wrong structure. where, again, all of our chemical bonds have to get divorces and all the electrons have to go back to the respective atom. So from this triple bond, 3 of those electrons are going to go onto oxygen. The other 3 electrons are going to go to carbon, and it's going to look like that. And then I'll draw boxes around all of the electrons that are assigned to each of those atoms. All right. So to calculate formal charge, we're going to do number of valence electrons minus the number of electrons each of those atoms has. So this number of valence electrons, these numbers are going to be the exact same as the other one we did, 6, 4, 6. Oxygen typically has 6, carbon has 4, the oxygen has 6. But then we actually, for the minus the electrons each atom has, we want to count the number of electrons actually in each of those boxes. So working left to right, that first oxygen has how many? 5, then 4, then 7. So when we do the subtraction, it is +1, 0, -1. Is that good? That is not good. So here we see, even though all of the atoms technically have satisfied octets, this is not the correct Lewis structure because we did not minimize formal charges. All right. So I hope, I know a lot of you are sitting there like thinking, oh, I already know that CO2 has 2 double bonds on it. But this is showing you, that proves why CO2 has 2 double bonds in it, because it is the structure that minimizes formal charges. So let's look at another example where we have to use formal charges to figure out what is the most correct, the most valid Lewis structure. So here's another compound, NCS anion. So let's go through the 6 steps. Here I'm specifically telling you that carbon is the central atom. Right, so let's go through the 6 steps. Get those valence electrons. Nitrogen has 5, carbon has 4, sulfur has 6, and then because it's an anion, we need to adjust the electron count. So are we going to remove an electron from the count or add an electron to the count because it's an anion? Add 1, yeah, so we're going to add 1 electron, and so when you add that up, I think it is 16. Right, that's what we're allowed to spend. So now we're going to move on to skeleton structure. So C is in the middle, because I told you it's in the middle. Then we have the N and the S, and I'm going to draw single bonds to each of them, right? But in drawing those bonds, how many electrons have I spent so far? 4, all right? So 4. Next, we spend the rest of our electrons and start placing electrons on outer atoms first, completing octets. And if we have any left over, put them on the central atom. So we have 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'm done. I've run out of electrons. But do we have a problem? Let's check octets here. Nitrogen has a satisfied octet. Sulfur has a satisfied octet, but does carbon? No. Am I allowed to just do this? No. So what do I have to do? Move lone pairs, make double bonds. Do you see how this kind of looks familiar from our other example? Yeah, but what's the problem here? We're going to move lone pairs to make double bonds, but there's multiple ways we can achieve that. Let me just ask you, how many additional bonds do I need to make to carbon to achieve an octet? 2 more, all right? So I have to move 2 lone pairs, but there's a bunch of ways I can achieve that. What is one of the ways I can achieve it? Is kind of like the same way that we finished CO2, is just take 1 lone pair from each of these each of the atoms, all right, and make it like this. And then I can draw what that looks like. Carbon in the middle, double bond, nitrogen, 2 lone pairs left over, sulfur, 2 lone pairs left over, right? But then how else could I complete this molecule? Carbon just needs 2 additional bonds, but couldn't both of those bonds just come from one of the atoms? Maybe both of them come from nitrogen? Yeah. So the complete Lewis structure could look like this, where there's a triple bond on nitrogen, and then we're left with 1 lone pair on nitrogen. Is that the only way we can finish it? Nope. We can also put the triple bond between carbon and sulfur instead. So the same idea, I just need 2 additional bonds to carbon, but this time they're going to come from sulfur. So that would put a triple bond on sulfur and carbon and leaving a single bond with carbon and nitrogen. So it would look like that. All right. So which one of those structures is correct? I don't know. So how can we determine which one is correct? We use formal charges. Yeah, so even I don't know which one is correct because I need to calculate the formal charges to figure out which one is correct. So we're gonna do the same thing, okay? We're gonna do how many electrons does each atom have in terms of valence electrons, and we're gonna subtract the number of electrons assigned to each of these atoms in the given Lewis structure. So that means all of the chemical bonds have to get divorces. All right, so it's gonna look like this. All right, I'm not gonna draw the boxes this time. I hope you can just count how many electrons are assigned to each atom. And then once we calculate this, it'll be much more clear which compound is, or which Lewis structure is the correct one. So we're gonna do valence electrons first. So nitrogen has 5, carbon has 4, sulfur has 6. So how many electrons are assigned to that nitrogen atom? 6, carbon has 4, sulfur has 6, perfect. Right, so it looks like our formal charges is -1, 0, 0. All right, and actually before I even do this, before we started calculating formal charges, if you actually look at the octets of all of these atoms, they all have 8. Right, they all have satisfied octets, but we're going further to see, okay, which structure is the most correct that minimizes formal charges. All right, so let's go again. 5, 4, 6 is the same across the top, but where the numbers do change is the numbers of electrons assigned to each of these atoms. Okay, how many electrons on nitrogen? 5, 4, 7. So in this structure where the triple bond is on nitrogen, formal charges are 0, 0, -1. Right? And then the last one, it's still 5, 4, 6, but here in this structure, nitrogen has 7 electrons, carbon has 4, sulfur has 5. So this one is -2, 0, +1. All right, so of these structures, which one is absolutely not correct? The last one. Do you see why the last one is not correct? The reason is because it doesn't minimize formal charges. We have some -2, +1 business going on. But then the 2 that are left over has the most zeros in it, all right? We have to have a negative formal charge somewhere because this compound is negatively charged, all right? But we have a choice. Do we want to put the negative charge on the nitrogen atom or on the sulfur atom? So we have a choice here. They're both basically minimized the same, but we have a choice of where to place that negative formal charge. And so do you remember the second criteria for formal charges? If you have to have a negative formal charge somewhere, where do you put that negative? On the atom that is most electronegative. Yeah, so think about electronegativity is the tendency for an atom to attract electrons to itself. So which of those atoms will attract electrons to itself? Nitrogen or sulfur? It's not going to be the sulfur. It's going to be the nitrogen atom. Do you remember with electronegativities, the high 5? Which elements are the high 5? Fluorine is the most electronegative. Then it is oxygen and nitrogen, and chlorine and bromine. All 5 of those elements will attract electrons to itself, has the highest electronegativity. So based upon that, the first structure is the correct structure, and it's because it places the negative formal charge on nitrogen, which is more electronegative than sulfur, all right? And so that is the most correct Lewis structure, all right? And so in these examples, the tricky part is that placing the double bonds is not as obvious where you should do it. And so you can always check your work if there's instances where you can, complete a Lewis structure multiple ways. You would have to calculate formal charges to figure out the most correct way, right? I will point out there was another example we did with other double bonds. So here's an example. We did carbon with 2 hydrogens and an oxygen here. In this example, it's not as useful, it's not as necessary to calculate formal charges for this molecule. And the reason is, let me just go back up to the compound we did, all right? When we did the skeleton structure for this molecule, and we recognize, oh, this carbon atom does not have a satisfied octet, we need to make an additional multiple bond. There's only one place that multiple bond can come from. It can only go between the carbon and oxygen. Because can you form a double bond between this hydrogen and carbon? You can't, because there are no like lone pairs on that hydrogen to move around. So in this case, there's only one place you can place a double bond. So it's not really necessary to calculate formal charges in this example, like it was for the other ones where it wasn't as obvious where that double bond should go. It's all decided on formal charges. All right, so yes, that's kind of one of the harder Lewis structures to draw. And so now we'll kind of look at some other interesting examples that come out of Lewis structures, and that is the idea of resonance structures. That sometimes when we're drawing Lewis structures, there's actually more than one valid structure that describes the molecule. Structures that have the same valid formal charges, all right? And here's an example, all right, ozone. Let's draw the Lewis structure for ozone. Ozone is 3 oxygen atoms, 18 valence electrons. So here I have my skeleton structure. Oxygen is central because it's all the same element bonded to one another. So let's follow the 6 steps. I drew 2 chemical bonds, so that's 4 electrons. So I want to put electrons on the outer atoms first and then on the inner atoms. So 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16. Where do those last 2 electrons go? On that central atom. All right, so let's check octets. Does this oxygen have a satisfied octet? Yes. Does this one? Yes, but does this one? No. So this central oxygen needs how many double bonds? Just 1. So I just need to move 1 lone pair, all right? But which oxygen's lone pair do I move? And so that idea that this oxygen, if I moved this lone pair to make a double bond on the left side of the molecule, or if I moved this lone pair on the right side of the molecule, both of these things are equivalent, all right? And so the idea is, you know, I can move 1 lone pair from one side, 1 lone pair from the other side. It doesn't matter which one I choose. The idea that there's multiple ways we can complete a Lewis structure where both of them are equivalent. So notice here that we have the double bond on this side, or we can have a double bond on this side. That idea shows that both of these Lewis structures are valid, and in real life, in nature, what we see is that both versions of those Lewis structures exist on this molecule at the same time. All right, so we can have the double bond on the left side or the right side. They're both equivalent. If you calculate formal charges, they're all equivalent. It's just kind of flipping back and forth. It looks like it's flipping back and forth, but truly it's not. So what we see is ozone is represented by a combination of these 2 Lewis structures. What we don't see is a short bond and a long bond on the other side. What we see are 2 bonds that have equivalent lengths, but they have properties between that of a double bond and a single bond. So what we say here is that this double bond is kind of like smeared across the entire molecule, that the double bond exists both on the left side and the right side of the molecule at the same time. So we can calculate bond order a different way here. So that double bond is not localized on one part of that molecule. It's spread across the entire molecule. So the bond order for this molecule ozone is actually 1.5. It's a little bit stronger than a single bond, but not as strong as a double bond. And so how we calculate resonance, bond order for resonance, is I like to look at the structure, recognize that, oh, this double bond can go on this side or on this side. And so you can calculate or count the number of bonds that are involved that are moving around in the structure over the number of positions. So in this case, a double bond and a single bond are swapping places. They're swapping places over 2 different positions. So this is 3/2, which is the same thing as 1.5. So this is how we get that 1.5 bond order, that in ozone, the oxygen-oxygen bond is between that of a single bond and a double bond. And so the important thing here is that those 2 bonds are identical. What I don't want you to think is that that double bond is flipping back and forth. It's not. That double bond actually exists on both sides at the same time. So really what we should draw is it should look like this, all right, where we kind of spread and smear that double bond across both of them. This is just very hard to draw in slides and stuff. So typically we draw it this way, where we draw both of the resonance structures that are present. So let's do another example of resonance. Let's do nitrate, right? Nitrate has a nitrogen, 3 oxygens. It's an anion, so we're going to add an electron. So our valence electron count here is, I think, 18. So we will go through our 6 steps. That's our valence electrons. So our skeleton structure will have nitrogen in the center. And then we'll have 3 oxygens around. All right, so I've drawn how many electrons so far? 6. So we can go up to 18. So I have 6 electrons I've drawn so far. I'm going to complete the octets on the outer oxygens first. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh, wait, hold on. What did I do wrong? It's 24, thank you. All right, that's why it didn't work. I ran out of electrons very soon. Okay, perfect, all right. I told you I'm not very good at simple math. So, okay, let's back up here. I'm allowed to spend 24, very good, because I ran out of money before I was done with my outer atoms. Okay, 24, I've drawn 6 already, so 6. All right, 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. All right, so I completed the octets of all of the oxygens, but I have no extra electrons for that central nitrogen, and that's a problem, because look at nitrogen. Does it have a complete octet? No, it needs how many more electrons? 2 more electrons. So I can achieve that by moving a set of electrons to make a double bond to nitrogen instead, all right? But here's the thing. So we need to make 1 double bond. But where is the double bond going to go? Can the double bond go here? Yes. But can the double bond come from over here? Yes. But can the double bond come from over here? Yes. All of these are equivalent. So basically this idea is I just need to make 1 double bond to that nitrogen atom, but there are 3 different ways I can achieve that. So what this nitrate ion have is 3 different resonance structures. So if you just scroll down to the next page, I have those 3 resonance structures drawn, right? Where notice 3 different structures. One has the double bond on the top, the other one has the double bond on the side, and the other one has the double bond on the side. All of these structures are equivalent, right? But when we look at a nitrate molecule like in real life, we won't find a short bond and 2 long bonds. That double bond is smeared across the entire molecule, all right? So if we go through all of these structures, and again, I'm just highlighting the importance and what to look for with resonance structures. Every atom follows the octet rule, technically, right? We also have the same formal charges on all 3 structures. All of them have equivalent formal charges, all right? They're all equivalent. So they're all correct. And so what we're not going to find is a short bond and 2 long bonds. We're going to find 3 NO bonds that are all the same length, because that double bond is smeared across the entire molecule, right? So let's predict what is the bond order for the bonds in nitrate. Are we going to find bonds that are bond order 1 and 2? No, we need to find a combined bond order for the idea of resonance, that double bond is smeared across the entire molecule. So let's calculate what is the bond order here. And here's my trick. all right, to calculate bond order for resonance structures is take the number of bonds that are moving around in the structure and divide by the number of positions. So in this example, we have a double bond that's moving around 3 different positions. So there's that double bond, a single bond, and another single bond, all moving around. Moving around 3 different positions. So this is 4 over 3. This is equal to 1.33. All right, so the bond order for the NO bond in nitrate, because that double bond is going across 3 different positions, is slightly stronger than a single bond, but not as strong as a double bond. It has a bond order of 1.33, right? So I want us to definitely be on the lookout for resonance structures. This will be a really important concept in organic chemistry. We'll look at some more examples in a little bit. So let's look at doing Lewis structures for some other molecules, some of those exceptions that I mentioned before. All right, so everything we've done up until now has followed the 6 steps very, very well, followed the octet rule really, really well. Here are just a handful of exceptions when it comes to Lewis structures. All right, so the first one is, mostly this is for octet rule exceptions. All right, so the first one is there are a few small elements like boron and beryllium that can have octet deficient central atoms, all right? So basically here, when boron is your central atom, it's okay that boron has 6 valence electrons. And here's an example, BF3. This is an example where boron has 6 electrons in its octet. Technically, it's octet deficient, but this is the correct Lewis structure for BF3. Right, so that's an exception. And beryllium, the same thing. Beryllium also can have 4 electrons in its octet, right? So those are 2 examples of compounds that can be electron deficient, and it's okay. Right, the second example of octet exceptions are any compounds that have odd number of valence electrons. If you have an odd number of valence electrons, it's impossible for every atom to have 8 electrons in its octet, right? So here's an example, NO2. If you count how many valence electrons there are, there's 17. We cannot in this class draw these Lewis structures. So this is outside the scope of this class. We'll never ask you odd number of valence electron compounds because we can't get those to have satisfied octets. And then the last one here, the third exception that we can do are very large elements that are period 3 or heavier that can undergo the phenomena called hypervalency, meaning that they can have expanded octets, right? Expanded octets means that the central atom has more than 8 electrons in its octet that it should typically have. So if we look at the sulfur atom, there's 1, 2, 3, 4, 5, 6 chemical bonds to that sulfur atom. This sulfur has 12 electrons in its octet. That's okay because sulfur is a period 3 element, and that's okay, right? Same thing for here, xenon F4. This xenon F4 has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons also in its octet. Right, and that is absolutely okay because xenon is I don't even know what period it's in. 1, 2, 3, 4, 5. It's a period 5 element. All right, so that's okay. So basically what we see here is that for very, very large elements, having expanded octets are okay. So let's look at a couple examples. Here's the thing. With these large elements, you're going to follow the same exact 6 rules, right? You're going to follow the same exact 6 rules. You're just going to count very, very carefully. So here are 2 examples where our central atoms go hypervalent, all right? So here's SF4, same 6 steps. We want to calculate number of electrons we're allowed to spend. So we have sulfur and 4 fluorines. That adds up to what? 28, 34? 34, yes? Okay, 34. And we're going to follow the same rules, okay? We're just going to count very, very carefully, all right? So we have sulfur in the middle, and then we have 4 fluorine atoms, 1, 2, 3, 4. Right? But with those chemical bonds, I've drawn 8 so far. So we got to count very, very carefully. So 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So I have 2 electrons left over. Where do they go? On the central atom. Yes. So this is why counting very carefully is important, because we need to know how many electrons go on that central atom. So now if you look at sulfur and count how many electrons sulfur has, that sulfur has 10 electrons in its octet. Is that okay? It is okay, because sulfur is an element that can go hypervalent, all right? So that is okay. So let's do the same thing for this BrF4- anion. So we have bromine, 4 fluorines, and it's an anion, so we're going to add an electron. So what is this? 36? So 36. All right. So same idea. Bromine, 4 fluorines. Count very carefully so we know how many electrons go on that central atom. Don't just spray and pray. You got to count very carefully. So we have 8 electrons so far. So 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. And so then how many lone pairs go on that bromine? 4 electrons, but paired up, so there's 2 of them, all right? So if you count, that central bromine atom has what, 1, 2, 3, 4, 5, has 12 electrons in its octet. Is that okay? Yes, it is okay, because bromine is a very large element. It's in period 4, all right? So those are some examples of the central atom exceeding its octet. You're going to see it sometimes for sulfur, bromine, iodine, and sometimes even noble gases like xenon can undergo hypervalency. Typically, these things will be attached, have fluorine attached to them as chemical bonds. So just know, count those valence electrons very carefully so you know how many electrons to put on that central atom. All right. So those are kind of like the last examples of Lewis structures. So these next 2 slides just kind of contain a lot of tips and exceptions for Lewis structures. But as long as you practice, you'll see a lot of trends come out. So example, like hydrogen is only ever going to form a single bond, right? That when hydrogen just has 1 single bond to it, its octet is complete. You don't have to think about adding more electrons around it. Hydrogen will never be your central atom. Or the halogens, they kind of act like hydrogen also, that they form a single bond to things, but they do have to have complete octets around them. But yeah, typically halogens will have 1 single bond. We tend to see multiple bonds occur for carbon, nitrogen, oxygen, or sometimes sulfur combined with carbon or oxygen. That's where you're going to start to see double bonds and where your central atom has an incomplete octet. Right? And then the exceptions we talked about, boron can be octet deficient, and that's okay. Beryllium also can be octet deficient. That one's not as common though. And then finally, period 3 elements like sulfur, bromine, xenon, those are all elements, all you can put iodine in there too, are central atoms that can exceed their octet, right? But if you follow the 6 steps, you'll just see it, that those central atoms do end up having more than 8 electrons surrounding it, and it's okay because those elements are very heavy and very large. All right, some tips to check your Lewis structure. Make sure, did you draw the correct number of electrons? All right, so look at your electron count, look at your picture, make sure those numbers match. When you follow the 6 steps, you will always be correct. Do all of your atoms have complete octets, aside for some of the exceptions that we talked about on the previous slide? And then finally, especially if you drew multiple bonds, are your formal charges minimized? That's what you want to look for. Typically, you only need to do that if you start drawing multiple bonds. And then finally, are there multiple ways to complete your Lewis structure? If that's so, typically there's oxygens present. This is where resonance structures are very important. And I think is the next slide talking about, nope, almost. Talking about resonance structures, because I want to talk about resonance structures a little bit deeper, because we'll look at more examples of that in the next chapter as well. I just wanted to talk about bond order and bond strength. We talked about bond strength in chapter 5, bond enthalpies, strength to break a chemical bond. So I'll just remind you that bond order just kind of tells us the magnitude of bond strength of these chemical bonds. So remember from chapter 5, we talked about strong bonds. Typically, these are short bonds. These have strong atom attraction to one another. They have very high bond enthalpies. So when we bring bond order into this, we see that as our bond order increases, so here's a NN single bond, double bond, triple bond, we see that as bond order increases, all right, length decreases, all right? So a bond order of 1, 2, 3, our bond lengths get smaller, 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 all right? But we also see strength increase. So a single bond is weaker than a double bond is weaker than a triple bond, but a triple bond is much shorter than a single bond, right? And so here's an example. Here's an NO double bond, has an enthalpy of 600 kilojoules, and here's an NO single bond, has a enthalpy of 200 kilojoules. So let's see if we can consider resonance here. So here's the resonance structures of NO3. Remember we talked about that just a couple minutes ago? So if I asked you to calculate or determine the NO bond enthalpies in a nitrate ion, what numbers would you expect to find? If you went into the lab and measured this, would you find bond enthalpies of 600 and 200 because there are double bonds and single bonds present, or are you going to find a different number? All right, so here if you look at these answers, 200 kilojoules, this is related to just one single bond. We're not going to find that because look, there's single bonds and double bonds. We're not going to find 600 kilojoules because that one is just the double bond. Are we going to find energies, bond enthalpies, energies of 200 and 600? Is that what we're going to find? We're not going to find that either because that indicates that, oh, you have I can't spell. Single bonds and double bonds. Is that what's present in the resonance structures of nitrate? Do we have discrete single bonds and discrete double bonds in a nitrate molecule? No, what did we learn? That double bond is actually smeared across the entire molecule, right? We don't have bonds that are bond order 1 and 2. What do we have instead? A bond order that is equal to 1.33. So what we're going to find are bond enthalpies that are between that of a single bond and a double bond. We're going to measure bond characteristics that are between a single bond and a double bond related to something with a bond order closer to 1.33. Right, and that's the idea of resonance structures, that we have to draw the double bond somewhere when we do these Lewis structures, but we have to understand that double bond actually exists in all 3 positions. Right, so let's just show, I'll show one more example of another resonance structure, a common one, benzene. Benzene is a molecule where we have 6 carbon atoms bonded together in a ring. And so in this ring, we have single bonds between carbon atoms and double bonds between carbon atoms. So notice in this first structure, if you just look at one of those carbon atoms, this one, does this carbon have a complete octet? Yes, so that carbon's good. What about the carbon next to it? Does this carbon have a complete octet? Yeah, so everything in this molecule has a complete octet, right? But what I want you to focus on is that the double bonds in this first structure between the carbon atoms are kind of arranged like this, right? But we don't have to put the double bonds between these 2 carbons and these 2 carbons. So what's next door here, I'm just showing you that we can draw an equivalent structure where the double bonds between carbon atoms are just kind of in this alternating place. And it's not that the double bonds are swapping places between these two carbon atoms, it's that the double bonds actually exist across the entire molecule all at the same time, right? So what you're not going to find is if you measure a benzene molecule, you're not going to measure, oh, a short, long, short, long, short, long carbon-carbon bond. No, instead, you're going to see all of those electrons delocalized across the entire ring. Oftentimes, benzene rings are drawn like this. It looks like a nut, where I'm just showing you that those double bonds are delocalized across the entire ring itself, where all of the carbon-carbon bonds are the exact same length across all 6 positions. So we don't actually have a bond order of 1 and 2 between these carbon atoms. Instead, what we find is resonance structures. So we can calculate the resonance structure here, bond order. There is a 3 double bonds and 3 single bonds, all swapping positions across 6 different positions. So if we wanted to calculate bond order, there's 3 double bonds and 3 single bonds swapping across 6 different positions. And so that is what, 6 plus 3 is 9. So this is 9 over 6. This is equal to 1.5. So what we see is that those carbon-carbon bonds have a bond order of 1.5. Those carbon-carbon bonds are a little bit stronger than a single bond, but a little bit weaker than a double bond. And that the consequence of that is those double bonds smearing across the entire molecule itself. That those double bonds are not localized in one place. They're smeared across the entire molecule, so they exist across all 6 positions. So it strengthens the carbon-carbon bonds a little bit. So we see benzene as a fairly stable structure. So there's another example of resonance structures. And then the last slide here of this chapter are other examples of resonance structures, where I only have one Lewis structure drawn, but I want you to recognize when calculating bond order, we need to consider different resonance structures that I didn't actually draw. So here's the first one. Carbonate is a very common resonance structure. So notice here's the complete structure of Lewis structure of carbonate. So notice I have a carbon. It has a satisfied octet and a double bond between this oxygen atom, all right? And then single bonds everywhere else. Do I have to put that double bond right here? If you kind of walk back and go back a step and think, okay, how could I have finished the octet on this carbon atom? Couldn't I make the double bond here? Couldn't I make the double bond here instead and turn this into a single bond, or make the double bond here? There are 3 different ways that you can draw that carbonate ion. So we could have the double bond there, or we could have the double bond here, or we could have the double bond there. All 3 of those are equivalent. So does this double bond just exist in this spot right here? Is it discrete? No, that double bond exists across all 3 positions. So let's see if we can't calculate the bond order of the CO bond in carbonate. All right, so how many bonds are moving around? There's a double bond and 2 single bonds. So there's 4 bonds moving across how many positions? 3. So this carbonate CO bond has a bond order of 1.33. Right, so those CO bonds, slightly stronger than a single bond, not as strong as a double bond. All right, let's look at acetate. Here's another example. Okay, notice carbon there in the center, it has a complete octet because there's a double bond to oxygen there. So it's the same idea. We have a carbon-oxygen double bond, but do I have to put that double bond there? Nope, where else can I put it? I can put it down here, but can I put the double bond here? You cannot. Why can't I put the double bond here? Because there are no lone pairs on this carbon atom. So in this example for acetate, there's only 2 resonance structures I can draw. One that has the double bond up here, and the other one has the double bond down there with the other oxygen. And this CH3 group has to remain the same, all right? So notice that this example only has 2 resonance structures. So let's go ahead and calculate what is the bond order for this example. How many total bonds are swapping places? 3, and how many positions? 2. So this acetate ion, the carbon-oxygen bond has a bond order of 1.5. Right? That is a common exam question. I can ask you, where I ask you which substance has the stronger CO bond, acetate ion or carbonate ion. That would require you to draw the Lewis structures. It would require you to calculate bond order and consider the Lewis and resonance structures. And we would get, oh, because acetate has a bond order of 1.55, that one has the stronger CO bond, all right? So that's how we could ask it on an exam. All right, let's keep going. Sulfate is another example of something that can undergo resonance. Do you kind of see the similarity between all of these? What do all of these ions have in common? They all have that oxygen atom. They have an oxygen atom that sometimes has a single bond, sometimes has a double bond. So look at this example. We have sulfur, 4 different oxygens around it. Notice that there are 2 double bonds and 2 single bonds. Do I have to put the 2 double bonds right there? Nope, I can put them here, I can put them here, I can put them here. There's a lot of different ways I can place those double bonds. So you can just have those 2 double bonds anywhere across those 4 different positions. So when we calculate bond order here, there's a double bond, another double bond, a single bond, and another single bond, rotating around 4 different positions. So this SO bond has a bond order of, I think, 1.5. All right. So those are all examples of resonance structures. And then I want you to understand, do you understand why formaldehyde does not have any resonance structures? Look, we have a carbon atom with a double bond, but can you put that double bond anywhere else? No, hydrogen cannot form double bonds. Typically what we're looking for are oxygen atoms. That's usually the thing that's going to signify, hey, you have a double bond going on. Right? So we'll look at some of the other consequences of resonance. It's really an interesting thing. You'll learn more about it in much more detail in organic chemistry, I promise. All right, so we got 30 minutes left. We're going to jump into chapter 9, but I'm going to point out that chapter 9 is basically just a continuation of chapter 8. We're still going to use Lewis structures. We're just going to expand on it, all right? So we just learned about the 6 steps. The 6 steps, Lewis structures. We're going to take those structures we've drawn and learn, okay, what do they look like in real life? What are their shapes, right? Because we've just drawn these molecules on paper. So now we want to think, what do these molecules look like in 3 dimensions? We're going to take those 3 dimensions and relate it to polarity. Are these molecules overall polar or nonpolar? Will they interact in an electric field or not? And then finally, we're going to move on to advanced bonding theories at the very end of this chapter. We're really going into detail about electrons in these last 3 chapters, and we'll kind of, capstone it all by looking at some advanced bonding theories. So we're going to learn something advanced. All right, so I need to announce that this chapter is very long. It's separated into 3 sections. First, we're going to look at shapes and polarity. Then we're going to look at the first advanced bonding theory, valence bond theory. And then the last advanced bonding theory is molecular orbital theory. But I'm going to point out that midterm 4 is going to get cut off right here. All right, so we all, as instructors, decided that we're going to just put MO theory on the final as to not try to rush through this chapter before midterm 4. All right, so we're not going to cover MO theory until after midterm 4. MO theory is actually one of my favorite things. So I'm happy to put it on the final because that allows me more time to talk about it. All right, so so chapter 9, we're just going to assess you on predicting shapes, polarity, and then the first advanced theory, valence bond theory. All right, okay, so we got to talk about shapes. What do molecules look like? All right, so the big idea here is that when drawing Lewis structures, we've been drawing them on paper, right? Paper is 2-dimensional, right? But molecules, they're not flat. They exist in 3D. Just because we draw a molecule flat does not mean that it's flat in real life. We have to remember that electrons, they repel one another, and that these molecules can exist in 3 dimensions. Just because you draw a molecule flat doesn't mean it's flat. So here's an example. Here's a carbon with 4 chlorines attached to it. So this could be, you know, the correct Lewis structure we did in chapter 8. You might notice, oh, these bond angles are 90 degrees, maybe? They're not. Just because we drew it 90 degrees doesn't mean it's actually 90 degrees in real life. We have to apply what we're going to learn about here is Vesper theory, the idea that electrons always repel one another, right? And this is how we're going to predict our shapes. So here's some other examples. Here's a molecule with this formula, AB2, so a central atom with 2 things bonded to it. Sometimes we see molecules that are linear with 2 things bonded to it. Sometimes we see them bent with 2 things that are bonded to it. Here's another example, AB3, a central atom with 3 things bonded to it. We get a bunch of different shapes. So how do we know which shape we get? Well, there's a very specific strategy we look at. There are some little bits of memorization that go along here, but I'll show you that in a second, all right? So what determines the shape of a molecule? The big idea here is that bonds are made of what? A chemical bond. Electrons. A lone pair is made of what? Electrons. Electrons are what charge? Negative. Negatively charged things are what? They are repelled by one another. So they want to get as close together or far away from one another as possible. Yes, as far away as possible. So this idea that if you look at a central atom and just count how many places do you find electron density, whether it be in bonds, whether it be in lone pairs, will dictate your electron geometry, all right? So what we have here is that the number of electron domains around a central atom is any region we find electron density. So this can be electrons in bonds or electrons in lone pairs, right? This is going to dictate what our electron domain geometry is. But notice that we're not differentiating between bonds and lone pairs. So in order to talk about what does a molecule look like, we can't see lone pairs, we only see atoms, we only see bonds. So that's where we cover up the places that are lone pairs because we can't see them, and then we only describe where the chemical bonds are, all right? So both of these things are related to each other. Where molecular domains, we ignore your lone pairs because we can't see them. But they're still there. That's the important thing, all right? So this idea of the electron domain geometry minimizes the repulsions. Your electrons spread out as efficiently as possible, all right? That is your template. And then we think, okay, which of those electron domains are actually chemical bonds? And then that will dictate what our molecular geometry is. All right, so this is what you need to memorize, okay? These are our electron geometry shapes. So notice that all of these shapes depend on how many electron domains there are around an atom. So the first step you should always do is count how many electron domains are around my atom, the central atom. So 2, 3, 4, 5, or 6. And that's what we're going to talk about here, all right? So like here's an example for 2 electron domains. Notice Be, beryllium with 2 things attached to it. This central beryllium has 2 bonds to it. So that's why there are 2 electron domains. Or here, BH3. This boron has 3 electron domains around it. This carbon atom has 1, 2, 3, 4 electron domains around it. 5 and 6, and so on, all right? So these are some shapes that you do need to memorize their names for, but the idea, these shapes come from the idea that electrons, they're gonna repel each other as efficiently as possible. So I have that kind of shown here with balloons. When we have 2 electron domains, we have 2 sets of electrons repelling each other as efficiently as possible. So with 2 electron domains, we see a linear geometry. If I asked you what is the angle between these 2 bonds, what would you say? 180, all right? So that's also a number that we need to know as well. Linear is 180. When we have 3 electron domains, it's like, I like to think of siblings who hate each other and they want to get away from one another as efficiently as possible. So here we have 3 domains of electrons trying to repel one another. And so we get this arrangement where all three domains are in a plane. So we call this trigonal planar. Planar because it's in a plane, trigonal because it makes a triangle, all right? So what is this bond angle between these two balloons? 120, all right? Okay, if we have 4 electron domains, this is where things get kind of weird, all right? This is where things start to be in 3 dimensions now, all right? This is not the best looking thing, but this is where 4 electron domains spread spread apart as efficiently as possible. We call this a tetrahedron, right? Because it exists in 3 dimensions. I should point out, let me show an actual molecule, might be a little bit easier. So this is actually what a tetrahedron looks like as well, where we have kind of like 3 feet sitting down and then 1 guy sitting up top here. All of these positions are equivalent. Like if I rotate it like this, it looks the exact same. It looks the exact same. 3 feet, 1 sticking up, 3 feet, 1 sticking up. All of these are equivalent to one another. It's in 3 dimensions. This bond angle is 109.5 degrees. Just memorize that number. Right? Okay, so that's 4 electron domains. Next is 5. This one's kind of harder to see. So this is 5 electron domains. We call this trigonal bipyramid. Trigonal, because if you look at it, let me show the molecule. The balloons are actually kind of harder to see. Trigonal bipyramid. There's 2 atoms that go up and down on the shape, but if you look at it down the axis, right? If you look at it down the axis, what shape do you see? A triangle. So we have like this triangle belt region and then an up-down axial position. So that's 5 electron domains. And then finally 6, all right? 6 is where every single electron domain is 90 degrees from one another. So if you kind of look down, it's like a square, all right? And you have this like up-down position, but they're all equivalent. They're all 90 degrees from one another, right? So those are our electron domain geometries, but notice I'm not distinguishing between bonds and lone pairs. So once we consider lone pairs, that some of those electron domains can be lone pairs, this is where we start to get what we call sub-geometries, right? So like, if I started with a trigonal planar electron domain geometry, but only 2 of them were bonds and 1 of them was a lone pair, we wouldn't be able to see this balloon. But we would see these 2. And so that brings us a new shape that would look bent, all right, where we can't see the lone pair, but we see the bonds that are actually there. So that's what we have in this graph. It kind of looks scary, but it's not really. So these 5 different shapes, these are the same electron geometries we showed in the previous slide. Linear, trigonal planar, tetrahedral, trigonal bipyramid, octahedral. And then this is the idea of, oh, we can start adding lone pairs to these shapes, all right? So if this trigonal planar shape has a lone pair, we're literally going to erase one of those lone pairs and ask ourselves what shape is left over. So let's look at that. Let's put a lone pair on this trigonal planar. If I just erase this, what shape is left over? It looks bent, right? And that's what we have right there. So notice that we can't see that lone pair. So we say the shape that's left over, it's bent. Or we can go to a tetrahedral, okay? Where let's put a lone pair on a tetrahedral, let's put it on one of the things, and let's say what shape is left. So we just take away that like top pointy part of the tetrahedron, and what's left is the triangle base. So we call that trigonal pyramid. Or we could have 2 lone pairs on a tetrahedron, but remember, we can't see those lone pairs. So what we get left with is a bent shape. What oftentimes people think is, oh, if I put 2 lone pairs on a tetrahedron, I get something that's linear. Remember that these electron geometries are our template for our molecular geometries, and that's a common mistake that I see. So let's just go through some examples. Of using these charts. You will need to know the names. You will need to know the bond angles for these, all right? So let's just practice those. And so the idea is you always want to start with your electron geometry and then think, actually, let's just go through all the steps, okay? First, draw your Lewis structure. Use Vesper theory on the central atom, meaning count how many electron domains you have. Get that electron geometry, that's your template. And then finally, to get your molecular geometry, take into account lone pairs. You can't see lone pairs, so just cover them up and ask yourself what shape is left over, all right, off of your electron geometry, right? So these are the steps. So I actually have all of the Lewis structures for us, so let's just go through these steps, all right? So here I have NH3. If you do the 6 steps, that's what you get. So let's look at that central atom. All right, that central nitrogen, count how many electron domains are there. You want to count bonds, you want to count lone pairs. So how many total bonds? 3, 1 lone pair, so the electron domain geometry is 4. Look back at that chart. An electron domain geometry of 4 is called a what? Tetrahedral, or TD for short, all right? So I will draw what that looks like. This is what a tetrahedral looks like, where the wedge means that bond is coming out of the page, and the dash means that other bond is going into the page. That's how I can try to draw in 3 dimensions, right? So that is our electron domain geometry, but we have a problem. Of that electron domain geometry, 3 of them are bonds, 1 of them is a lone pair. All right, so we want to take this electron geometry that I just drew, all right, that's a tetrahedral. How many of those bonds or how many of those domains do I need to cover up? 1 of them, because 1 of them is a lone pair, so literally what you're going to do is just erase 1 of them. So you notice that that was a lone pair, that was a lone pair. We can't see it, right? So we're just going to erase it and then say what shape is left over. It's like a triangle base. So we call this trigonal pyramid, or it's like trigonal pyramidal or something. Trigonal pyramidal. All right. So that's our strategy. So let's do this again for CH4. So tell me, what is the electron domain geometry? 4, we call that a tetrahedron. So let's be hyper specific. Of those 4 electron domains, 4 are bonds, 0 are lone pairs. So when we do our molecular geometry, do we have to account for any lone pairs? Nope, everything is a bond. So that means our molecular geometry is also tetrahedral, right? Just to prove it to you, I can draw that tetrahedron. Every single one is a bond, so we don't have to do any erasing business, right? But let's look at the next one, because we do have lone pairs we have to account for. Water. How many electron domains? 4. It is, again, tetrahedral, but this one's a little bit different. 2 bonds, 2 lone pairs. So again, we want to start with our electron domain geometry, but how many legs are we going to erase this time? 2 of them. We're going to erase 2 of them. So 2 of them are lone pairs. I'm going to put 1 right there, and I'll put 1 going backwards over there, right? Those are my 2 lone pairs. So I'm just going to go ahead and erase them and ask you what shape is left over. What is that? That is a bent shape. So do you see how it's bent? So what we see here is that water is bent, right? Specifically, it's bent where the bond angle is around 109.5. Because what we'll see here is there's another bond angle, I think the next one, that is also bent, but the shape is a little bit different. So let's look at this one, ozone. All right, so let's look at the central atom. Notice there's a double bond and a single bond. That double bond counts as 1 electron domain, all right? 1 electron domain. And the reason is because there's 4 electrons all in the same region, all right? So those 4 clustered electrons are going to behave the same as the 2 electrons in this single bond or the 2 electrons in that lone pair. So around the oxygen in ozone, there is only 3 electron domains, right? So when we talk about bonds in electron domains, a single bond counts the same as a double bond, counts the same as a triple bond, right? So let me give you another example. If I had something like this, all right, if I had a single bond there, a double bond there, a triple bond there, this isn't a real thing. Whoops. All right. All right, tell me how many electron domains are around that central atom, X. Remember what I just said. A single bond, a double bond, and a triple bond all count as one electron domain. So there is one domain, there is one domain, there is one domain, there is one domain. So this has 4 electron domains around it. All right, so it would have an electron geometry of a tetrahedral. Okay, all right, so let's go back to this. Ozone has 3 electron domains. Of that, let's just be super specific, 2 bonds, 1 lone pair. All right, so go back to the slide prior. What is 3 electron domains called? Trigonal planar, yes, trigonal planar. So let's go ahead and draw that. 1, 2, 3, right? What are the approximate angles between those domains? I asked you, 120, very good. But is that my molecular geometry? It is not, because one of those domains is a lone pair, which we can't see. So we're going to erase one of those, literally erase it, okay? Erase that lone pair. And then what shape is left over? Bent. But what is the approximate bond angle for this bent structure? It's going to be around 120 degrees. And the reason is because its parent structure is trigonal planar. So notice that we have 2 examples of bent structures. Here's a bent structure. Water is a bent structure, but they're slightly different. The ozone bent structure is closer to 120 degrees, and the water's bent structure is closer to 109 degrees. All right, and the reason is because they have different parent structures, different electron domain parent structures. All right, let's keep going. Okay, nitrogen has how many electron domains? 3. We call that what? Trigonal planar. Are there any lone pairs to worry about? Nope, so that means its molecular geometry is also going to be trigonal planar. All right, next one, BF3. How many electron domains? 3. What do we call that? Trigonal planar. All right, no lone pairs, so also trigonal planar. All right, so again, 0 lone pairs, 0 lone pairs. So what we see is any geometry that has no lone pairs on that central atom, your electron geometry is going to be the same as your molecular geometry. It's only when we have lone pairs we got to start covering up parts of our electron geometry to get that molecular. All right, last one. SF6, how many electron domains? 6. What do we call that? Octahedral. So that's the last one with 6 electron domains. Since there's 0 lone pairs, our molecular geometry is also octahedral because of no lone pairs. Every single electron domain is a bonding domain. We have a chemical bond in each of those, right? So all of this has to do with first starting with the correct Lewis structure, being able to interpret, okay, what are my electron domains around my central atom, and then applying lone pairs if applicable for that specific Lewis structure. All right, so we talked about, bond angles. All right, trigonal planar is usually 120 degrees. Octahedrals have what bond angles? 90 degrees. Tetrahedrals have 109.5 degrees, right? Those are all ideal bond angles, okay? So let's look at some deviations from ideal bond angles, and some examples include lone pairs, right? So in general, when we have electrons in a chemical bond, those electrons are really tightly concentrated in that chemical bond. But once you put electrons in a lone pair, all right, those electrons are more fluffy, they take up more space. I like to think they're big, fat, and juicy, and they push everything away from it, right? Because electrons, they do what? They repel one another, all right? So this is what happens, right? All right, so we have a bunch of molecules with tetrahedral electron geometries. They just have different number of lone pairs. So look here. CH4 has 0 lone pairs, so each of its bond angles are exactly 109.5. But once we put 1 lone pair on that central atom, so here's an example, here's NH3, notice what happens to the bond angle. It decreases, it's 107. Or let's look at water. Water has 2 lone pairs. It's still a electron geometry of tetrahedral. Look what happens to that bond angle. It gets even smaller. The reason, okay, is because lone pairs are big, fat, and juicy, and they push things away from it, all right? So here, this lone pair on this nitrogen atom is pushing these hydrogen atoms closer together, closing, making this bond angle a little bit smaller. And then in water, water has two lone pairs that are pushing these hydrogen atoms closer together, so the bond angle deviates even more away from that perfect 109.5. Right? So that's the idea of deviations. Lone pairs are just bigger than covalent bonds. So oftentimes what happens is lone pairs will decrease bond angles that are the opposite side of your atom. So let's look at an example down here, right? Yeah, okay, so here's an example. Let's look at this molecule. So here's a carbon atom with a double bond and two single bonds. So if we looked at that carbon atom, there are 3 electron domains around that carbon atom. So we would call that trigonal planar, right? It would have an ideal bond angle of 120 degrees. Okay, that's the ideal bond angle across all of these different bonds. But we have some weird stuff going around, all right? So just like I said, lone pairs take up more room. What do you think takes up more room? A single bond that contains 2 electrons, or a double bond that includes 4 electrons? What do you think? A double bond, yeah. So what we see here is that the double bond where the carbon and oxygen is takes up more room. Just takes up more room. So what's going to happen to this chlorine-carbon-chlorine bond? They're going to get closer together, all right? So this bond gets smaller. The bond on this side actually gets larger because of that carbon-oxygen double bond. So the most reasonable bond angle for the chlorine-chlorine bond is going to be slightly less than 120 degrees because this double bond just takes up more room and it pushes those bonds closer together, right? So this is a common exam question that we see, all right? Is like order these 3 bonds in order of degrees, right? So let's just kind of go about the strategy here. I have 3 different bond angles marked, and we want to determine what is the bond angle. So we need to consider, 1, the ideal bond angles and any deviations away from those ideal bond angles. So my first strategy is to look at each of these central atoms and ask myself, what are the ideal bond angles here, right? So this central oxygen atom has 4 electron domains. What do we call that? A tetrahedron. And tetrahedrons have 109.5 degree, like the exact ideal bond angle, right? But what's the problem here? We have 2 lone pairs. So are we actually going to measure exactly 109.5? No, we're going to measure what? A bond angle smaller or larger than 109.5? Smaller. Yeah, it's going to be a lot smaller because there's 2 double bonds. Or sorry, two lone pairs. All right, let's look at these 2 carbon atoms. Right? This carbon atom has how many electron domains? 3. Okay, what do we call that shape? Trigonal planar. And then what is the ideal bond angle there? 120. Okay, but we got to be careful here. Notice this, this double bond here. Maybe it would be easier if I drew it this way, where it's more like trigonal planar. I'm asking you, what is this bond angle? Is that bond angle going to be exactly 120 degrees? Is it going to be smaller than 120 degrees? No, it's actually going to be slightly larger than 120 degrees. All right, this one's going to be slightly larger because of, I'm asking you this bond angle that's next to that double bond. If I would have asked you what is this bond angle on this side, the opposite side of the double bond, this one would be smaller than 120 degrees, all right? But that's not the one I'm asking you, all right? And then the last one here, bond angle 3, all right? This last bond angle, again, 3 electron domains. We call this trigonal planar. In a perfect world, it would be 120 degrees, right? But because this bond deviates a little bit because of that double bond, it's actually going to be slightly larger than 120 degrees. So those are our estimates for our 3 bond angles. So the first one is a lot less than 109.5 degrees, and then these two are about the same, slightly greater than 120 degrees. All right. So yeah, that's a great place to stop. So definitely in those next 2 days, practice those 6 steps for Lewis structures, because we're going to continue to use these steps and ideas for the remainder of this chapter.